Hi, I'm Dr. Billy Wu, and in this video we'll explore the science behind sodium-ion batteries and discuss whether or not they're the low-cost future of energy storage. Firstly, we're almost certainly going to see an increase in battery-powered devices in the future, ranging from small micro e-mobility applications such as e-bikes, increasing to larger electric vehicles with battery packs around 100 times larger, to grid-scale batteries, which can be several megawatt hours to help balance intermittent renewable solar and wind energy. Therefore, to realize this future, we're going to need more batteries, with lithium-ion batteries being the current technology of choice. Here, you can see that there was about 750 gigawatt hours worth of production in 2020, with this forecasted to increase to at least 3.4 terawatt hours by 2030. Now, whilst these exact numbers are more than likely going to change in the coming years, I think we can safely assume that there will be a huge increase in market size for batteries driven by the transition to a net zero carbon future. However, a key question is, do we have enough raw materials to meet this demand? Here, you can see one forecast which suggests that in the coming years, lithium supply could struggle to keep pace with demand. To start to answer this question, let's have a look at the relative abundance of different elements in the Earth's crust. Here, you can see that there's approximately 20 parts per million of lithium, which is relatively low compared to other elements. An alternative to the lithium-ion battery is the sodium-ion battery. Here, you can see that there's about 23,000 parts per million of sodium in the Earth's crust, which is over 1,000 times more than lithium. Of course, there are other metals to consider in a battery, including nickel, but this analysis gives the first indication of what materials we should be considering if we want to use Earth-abundant materials. Of course, the abundance of materials varies with different locations, so let's have a look at a specific example. For lithium, one of the main sources is from brines, with Chile one of the main producers. Here you can see that typically there might be around 0.04 weight% lithium in these brines compared with sodium, which has a concentration of around 9 weight%, which is over 200 times greater. For lithium-ion batteries, other key metals include nickel, manganese, cobalt, aluminium, and copper. Now, for primary production, iron is by far the most mined metal, followed by aluminium. Copper is used as an anode current collector and is produced in a reasonable amount, but demand will likely be high as these are needed in electric motors, transmission lines, and other applications. In the case of nickel and cobalt, which are used in high energy dense batteries, there are some supply concerns. Of course, there are also metals produced by co-production, but the amount of material here isn't as significant. Therefore, not only do we need to find alternatives to lithium, but also for metals such as nickel and cobalt. Therefore, driven by these considerations, sodium-ion batteries are being developed due to their potential cost, safety, sustainability, and performance advantages over traditional lithium-ion batteries. These batteries can be made with widely available and inexpensive materials, with sodium being significantly more abundant than lithium. Furthermore, sodium-ion batteries can use aluminium for the anode current collector instead of copper used in lithium-ion cells. This ultimately reduces the supply chain risks. Furthermore, they can be safer than lithium-ion batteries as they can be stored at 0 volts, posing less risk during transportation. Here, traditional lithium-ion batteries are generally stored at around 30% state of charge. Also, the electrolytes used in sodium-ion systems generally have a higher flash point than lithium-ion battery systems, reducing flammability risks. Another advantage is that the process for making sodium-ion batteries is very similar to that of lithium-ion, meaning that the scale-up of the technology can benefit from the work already done in lithium-ion batteries. When we compare the different performance characteristics, we can see the general pros and cons of each technology. Right now, the energy density for sodium-ion batteries is still lower than high-energy lithium-ion cells, which use nickel, but they are approaching the energy density of high-power lithium iron phosphate cells. The cycle life of cells is reasonable in some configurations, but one of the interesting elements is that sodium-ion batteries can have quite high power characteristics. Now, it's useful to go into a bit more detail to understand why in some cases the comparison in properties between lithium-ion might not be as straightforward as initially expected. First of all, people say that sodium is a heavier element than lithium, and it is, with an atomic weight 3.3 times greater. However, it's important to note that lithium or sodium in a battery only accounts for a small amount of the cell mass, and that the energy density is mostly defined by the electrode materials and other components in the cell. In that sense, while current sodium-ion batteries have relatively low energy densities, there is the potential for this to increase in the coming years. Another advantage is that a sodium-ion battery uses aluminium for the anode current collector rather than copper, which is around 75% less dense and is also cheaper. Now, it's important to remember that there are a number of different lithium-ion and sodium-ion battery configurations. However, if we caveat this, it's useful to put some numbers to each technology to allow us to compare them. For specific energy, high nickel lithium-ion batteries are generally at around 270 watt-hours per kilogram. For high power lithium iron phosphate cells, this is more at around 170 watt-hours per kilogram. For a sodium-ion battery with a layered metal oxide cathode and hard carbon anode, there have been reports of specific energies of around 160 watt-hours per kilogram, which is very respectable. However, when we look at the volumetric energy density, we can see that improvements are still needed, in part due to the low density of hard carbon compared to graphite. This is not too far away from lithium iron phosphate, however quite far away from NMC lithium ion cells. For gravimetric and volumetric power density, you can see that sodium ion has some clear advantages due to the high sodium ion mobility in the electrodes. And for lifetime, there are some clear advantages also. However, this depends heavily on many factors and this table should not be taken as universal. Now, one of the key arguments for the use of sodium-ion batteries is that they're lower cost, and this deserves a bit more discussion. It's been estimated that at scale, a sodium-ion battery with a layered metal oxide cathode and hard carbon anode will have 25 to 30% lower material costs than a lithium iron phosphate battery. If we unpack this a bit more, we know that two of the main differences in a sodium-ion cell versus a lithium-ion cell is that they replace lithium and copper with cheaper sodium and aluminium, which gives around a 12% cost reduction, with most of this being due to the aluminium current collector. As mentioned earlier, most of the cost of a cell will be defined by the electrode materials. Here, for sodium-ion, hard carbon is emerging as one of the most popular materials. However, because hard carbon has a lower density than graphite used in lithium-ion batteries, this means that for the same amount of active material, you'll need to use more electrolyte, which adds cost and mass. Furthermore, hard carbon is generally more expensive than natural graphite, with some hard carbons having lower performance than graphite. If we then compare the costs of different lithium-ion and sodium-ion battery configurations, we can see that there are potential cost advantages, but the exact number depends heavily on the chemistry being used. Here, we compare three popular lithium-ion battery chemistries, LFP, NCA, and NMC, with different sodium-ion battery configurations. Here, in the near term, this is likely to be a battery with a sodium layered metal oxide cathode with a hard carbon anode, but in the future, the cathode may well improve, with some viewing future anodes as having a blend of phosphorus which has a higher specific capacity. However, when interpreting these numbers, it's important to note that material prices do vary and there's uncertainty around future material performance. Now, in terms of where we might see these batteries, it's important to note that right now, the energy density and lifetime of sodium-ion cells still generally needs improving. But we're likely to see some early pilot applications and potentially early adoption in stationary energy storage units. Then, maybe within a few years, we might start to see them in power tools and backup power applications before finding more e-mobility applications such as e-scooters, e-bikes, and light electric vehicles. Here, it's important to note that innovation and scale-up in materials takes time. This plot here shows what the Joint Center for Energy Storage Research in the US calls the battery technology readiness levels, where from scientific breakthrough to full commercialization, this process can take up to 10 years to prove performance and scale processes. Now that we've covered the general aspects of sodium-ion batteries, it's worth doing a bit of a deep dive into the performance of different types of sodium-ion batteries. In order to do that, we'll first revisit what's inside a lithium-ion battery. If we look inside one, what we'll find is several layers of battery materials including a copper current collector, a porous anode normally made of graphite, a porous polymer separator, a porous cathode normally made of a transition metal oxide, and an aluminium current collector, all immersed in a liquid electrolyte. When a battery is being discharged, lithium ions are removed from the anode and moved towards the cathode. The electron, which is released from this process, goes around an external circuit where useful electrical work can be extracted. The reverse then happens when the battery is charged, and this back and forth movement of lithium ions is called the rocking chair mechanism. A sodium-ion battery has a similar design but with slightly different materials. Notably, sodium is used as the charge carrier as opposed to lithium, and aluminium is used on the anode current collector instead of copper. Now, since sodium has replaced lithium, we have to use different materials in the anode and cathode. Here, a key difference between the two ions is that sodium ions have a larger atomic radii than lithium ions. The larger ion can affect the stability of the electrode crystal structure and also impacts the transport properties, which is how fast the ions move through the electrode. In terms of how a sodium-ion battery works, this is essentially the same as a lithium-ion cell. When fully charged, sodium ions sit in the anode, and when discharged, they move to the cathode with the electron again moving around an external circuit. This process is then reversed when charging. Comparing materials between lithium-ion and sodium-ion batteries, we can see that lithium-ion cathodes commonly use materials such as lithium iron phosphate, lithium nickel manganese cobalt oxide, and lithium cobalt oxide. For sodium-ion batteries, the most common cathodes include layered transition metal oxides, Prussian blue analogues, and polyanion compounds. Here, both lithium-ion and sodium-ion cathodes use the same aluminium current collector, PVDF binder, and conductive carbon. For lithium-ion battery anodes, materials such as graphite, silicon, and lithium metal are used, often with a CMC and SBR binder and copper current collector. For a sodium-ion battery, some potential anode materials include hard and soft carbon alongside sodium metal. Here, PVDF binders and an aluminium current collector is used, with conductive carbon being used in both systems. Finally, for the electrolyte, lithium-ion batteries generally use a lithium hexafluorophosphate salt, whereas sodium-ion batteries generally use a sodium hexafluorophosphate salt. Here, the solvent can come from the same or similar carbonate family. Next, we focus on the three main cathode materials. Here, layered transition metal oxides, similar to the NMC lithium-ion battery cathodes, generally have the best specific energy with reasonable cycle life. Their conductivity is good, giving them good power capabilities, but the materials can be air sensitive and improvements to cycling stability are still needed. Next, Prussian blue analogues have potentially good cycle life due to their robust crystal structure, which also enables high power capability. However, these materials generally have low specific capacity both volumetrically and gravimetrically. Finally, polyanion compounds can also have good cycle life due to a robust crystal structure, but again, low specific capacity. In addition to this, these materials generally have low electrical conductivity. However, they can have quite high voltages and good thermal stability, giving rise to better safety characteristics. Here, it's important to note that cathode materials are still under development and improvements are likely to continue. And also different materials are likely to be suitable for different applications. Delving even deeper into layered transition metal oxides, these generally have high specific capacities and good power characteristics due to good electronic and sodium ion conductivity. However, as we insert and remove sodium ions, this can lead to reasonable volume change and poor lifetime if not managed. Here, there are two main types of layered transition metal oxides, which are classed based on whether sodium resides in a prismatic or octahedral crystallographic site. These are therefore termed P and O type materials, followed by an index which indicates the number of metal oxide layers needed to make a repeating unit, with P2 and O3 type cathodes the most common. Whilst exact properties vary, P2 type cathodes generally have better power and stability, and O3 type cathodes generally have higher specific capacity. However, a problem with this class of material is that they tend to be air and moisture sensitive, with water inserting into the sodium layers reducing performance. Next, with Prussian blue analogues, these materials have a similar crystal structure to Prussian blue synthetic pigments. They generally have a robust crystal structure which potentially enables long lifetime, with this open structure enabling good sodium-ion conductivity, but the poor electronic conductivity needs to be overcome for high power capability. A drawback of this open structure, however, is that it reduces the energy density of the material. However, many Prussian blue analogues use earth-abundant metals such as manganese and iron, making them potentially quite low cost. However, there can be problems in that some synthesis routes can result in water existing in the structure of the material, which can react with the electrolyte in a fuel cell, reducing the lifetime. Finally, we have the polyanion family of materials which generally have higher operating voltages than other materials. Their robust crystal structure can provide good lifetime, and the strong bonding with the oxygen in the structure improves their safety characteristics. However, the specific capacity is generally lower than metal oxides, and their low electronic conductivity usually means they need to be carbon coated. Here, there are a number of different types of material, each with their pros and cons, including phosphates, pyrophosphates, fluorophosphates, mixed phosphates, sulfates, and silicates. To visualize how each class of materials compares against each other, this plot shows the typical average voltage of each cathode with their general specific capacity. Note that the exact numbers can vary depending on a range of factors. For the metal oxides, which we can break down into P2 and O3 type materials, these generally have the highest specific capacity. Prussian blue analogues have somewhat lower specific capacities, but have a more theoretically stable crystal structure which can give better lifetime, not shown on this plot. And the polyanion compounds generally have the lowest specific capacity, but highest voltage and improved safety, again not shown on this plot. Again, it's important to note that not all possible materials are shown here. Next, for anode materials, there are generally three main types. Carbonaceous materials, where hard carbon is perhaps the most popular. This has reasonable specific capacity and good lifetime. Metal oxides and sulfides generally have much higher specific capacities, but their lifetime can be poor. And similarly, alloying materials such as tin and phosphorus have again high specific capacities and poor lifetime, with alloying materials experiencing significant volume change during cycling, leading to mechanical polarization of the electrode and poor lifetime. Here, there are three main ways sodium is stored in the electrode: insertion, conversion, and alloying. Again, if we plot these materials on a chart of voltage versus specific capacity, we can more easily compare them, noting that for anodes we want a low voltage and a high specific capacity. Here we can see that alloying materials generally have the highest specific capacity, though they have poor lifetimes. Metal oxides and sulfides can also have high specific capacities, but generally low lifetimes. And carbonaceous anodes such as hard carbon have a reasonable specific capacity, but with generally good lifetime, which has resulted in their likely first commercialization. Now, given that hard carbon is the most likely first anode material for commercially viable sodium-ion batteries, it's worth spending a bit more time discussing them. Here, hard carbon has randomly orientated graphitic domains with a higher interlayer spacing than graphite. Hard carbon can be made from different carbonaceous precursors such as biomass and certain polymers through a heat treatment process, which results in non-graphitizable structures even at high temperatures. These materials often have a high surface area and porosity with lots of defects, which results in multiple different ways sodium ions can be stored in their structure. However, because of this high porosity, the density of hard carbon is generally low, resulting in poor volumetric specific capacity. So, in summary, sodium-ion batteries have the potential to offer a low-cost, sustainable and safer alternative to lithium-ion batteries. This comes about through the use of materials which are more abundant, reducing supply chain issues. They use cheaper and less dense aluminium on the anode current collector, which can reduce cost. Also, because the battery can be stored at 0 volts, this improves their safety, and they can often use electrolytes with a higher flash point, reducing flammability issues. In some electrode materials, the conductivity can be quite high, giving them good power characteristics. Here, the main cathode materials are layered metal oxides, Prussian blue analogues, and polyanion compounds, with layered metal oxides generally having the highest specific capacity, though Prussian blue analogues have potentially good cycling stability and polyanion compounds good thermal stability. The main anode materials include carbonaceous, metal oxide, and sulfides, as well as alloys, with hard carbon being the most likely to be commercialized first due to its reasonable specific capacity and good lifetime. However, it's important to note that energy density is still low compared to lithium-ion, but it is improving. Finally, I think that sodium-ion batteries are unlikely to completely displace lithium-ion batteries, but rather they will be complementary to them as overall demand for batteries increase. So, I hope that this video has been a useful introduction to sodium-ion batteries. There are lots of developments in the field, so many of these generalizations are likely to change in the coming years, but I believe that we will soon see these batteries being commercialized, with them being complementary to lithium-ion batteries.